Hi, we're going to be talking about Hadoop today. I will assume for the purpose of this talk that you don't have any experience in the topic, but if you do have some experience with Hadoop or its general ecosystem, that's awesome. What we'll do, however, in today's talk is look at it from a 30,000-foot overview. So my name is Kevin Fiesel. I am a manager of a predictive analytics team in Durham, North Carolina. I'm also a Microsoft Data Platform MVP, and I have a blog, Curated SQL. The idea behind Curated SQL is that I want to try to find and link to 5 to 10 interesting blog posts per day. Now, interesting can be database administration or development. It could be Hadoop. It could be Python, R, security, basically this entire broad data platform space. So that's curatedsql.com. The way that this will work is I'm going to start off with a basic overview of what Hadoop is, and then we're going to look at 4 historical timeframes. And during these timeframes, we'll get an idea of what the Hadoop ecosystem looked like and some of the causes for why it looked that way. So we'll start with this basic overview. Hadoop started early on, pre-Hadoop itself, with a couple of Google research papers. One was on a concept called the Google Distributed File System, which was a file system that could be distributed across a number of machines. And the other was on a programming technique called MapReduce, the combination of a couple of functional programming concepts. So we'll talk in more detail about both of these in just a bit. In around that time, Doug Cutting was working at Yahoo. Cutting needed to solve similar problems to what Google had. In other words, lots and lots of search data and also relatively unstructured pages, web pages that needed to be parsed. So these techniques that Google was coming out with fit pretty well with what Cutting needed to solve. And so at Yahoo, they developed an actual implementation and open sourced it as Hadoop. Since then, it's taken off and become pretty popular among a number of larger tech companies, and then it's moved into a space for larger corporations and getting into medium-sized corporations as well. There are several great use cases for Hadoop. Hadoop is not a one-size-fits-all, move everything to it type of technology, but it does have a particular set of fantastic spaces where it can help you solve problems. The classic scenario is what we'll talk about first, and that is batch processing of very large amounts of data across a large number of machines. So that's what people have in mind when they talk about Hadoop. Since then, we've seen it move into a couple of other interesting spaces. The first one is a cold storage of data that you would normally have in a transactional system. So you may store a few years of data in your transactional system because people actually access that. But then as you go back further and further, you may not need all of that data except when an auditor comes by. So you have to store it, but it doesn't have to be directly accessible. One way that you can get around that is doing something simple like save the files off to tape or to some permanent medium and ship it off someplace. When the auditor comes, you can recover the data and you'll have it available. Another similar example that doesn't involve tape drives is putting out to S3 Glacier or Azure Blob Storage. So you have this data that's kind of permanently stored on the internet, and when you need it, you can pull it down, knowing that it's going to take a while to get that data back, and it'll take a while to write any query against that data. Hadoop provides us a similar scenario where I have my expensive transactional system. Maybe I've got all-flash arrays. Maybe I'm using NVMe drives to store this data. That's very expensive. By contrast, I might have some spinning disk sand somewhere, and I can just dump the files off onto there and make it accessible through Hadoop. So I can expose it so when the auditor does come, we don't have to worry about waiting several hours or maybe a couple of days to get this data back. Just write a query, realizing the query will take a bit longer than it would on your transactional system. But if you're willing to accept that longer time for churn, this is a good solution. A third space where we've seen Hadoop really take off is in streaming data. So this is almost the opposite of the first scenario. So in our first scenario, we have lots of batch data, gigantic files, terabytes, possibly petabytes of data we're trying to churn through. By contrast, the third example here, this real-time ETL and streaming, think of it as millions of small devices, IoT devices, sending messages to our servers. We need to have something that kind of intercepts those messages and will allow us to process those messages very quickly. And it turns out the Hadoop ecosystem works fantastic for that scenario as well. Before you get into Hadoop, there are a few prerequisites. If you're going to be a developer in this stack, I very highly recommend that you know Java. Now, you don't have to know Java absolutely. I personally don't like Java very much, but it is the lingua franca of Hadoop. You can get around it a bit by writing in Scala if you're a functional programming fan, or Python if you already have that data science background and you already develop in Python. You might even get away with some .NET code, C# or F#, but eventually you're going to want to know Java. The second language, SQL. Some variant of SQL powers a large portion of the Hadoop ecosystem. So we have Hive, which is SQL on Hadoop. It's warehousing sitting on a Hadoop cluster. We have Spark SQL, which is a SQL implementation on Spark, which we'll talk about later. There's also HBase, which is a NoSQL database, but it has Phoenix, which is a relational component sitting on top of the NoSQL database. So it seems no matter where you go, eventually you will come back to SQL. That's a good language to know for any sort of ad hoc query processing. The third thing that I want you to know is some form of shell scripting. So my preference is Bash, but if you're a Corn Shell fan or a Z Shell or C Shell or something else, that's cool. You can go with that. If you don't know what any of those are, I'd recommend learning Bash. It's probably the easiest to learn, and you'll have the most examples on the internet regarding it. Finally, no Linux. There were implementations of Hadoop on Windows. Hortonworks Data Platform had a Windows edition. Thankfully, mercifully, they killed that thing off. Everybody uses Linux in the Hadoop space. You don't have to write using a Linux laptop or a desktop, but your servers are going to be running some flavor of Linux or possibly a Unix variant. Just realize that everybody uses this. I want to wrap up this section with a little bit of levity. As a warning, many of these products have very similar names to Pokemon. For example, on my screen I have Apache Metron, and I also have the Pokemon Magneton. If you are a fan of the Pokemon series of games, you'll probably have a lot of fun with this, or possibly get a little bit confused. But at the end, I'll give you a link to a resource that includes a game that is big data or Pokemon, and it will allow you to decide, given this name, whether it's a big data technology or a Pokemon character. So have fun with that. And now let's go on to the next section. So now we're going to look at the birth of Hadoop. This is the first few years of Hadoop's existence. To understand why Hadoop is the way that it is, we have to go back to those years, that 2007 timeframe, and talk about what hardware looked like at that point. For the companies that we're initially looking at, the Googles, Facebooks, Yahoos of the world, a lot of their servers were off-the-shelf stuff. They didn't have custom-built devices like they do today. Instead, it was buy a bunch of HP and Dell and IBM machines. Sometimes throw a bunch of stuff together in the same data center. So you have dozens of off-the-shelf servers with direct attached storage. This was before SANs were really popular for this type of problem. The storage on these servers was primarily spinning disk. Pre-SSD, so it's going to be slow. Servers were on-prem. This was, 2007. It was right around the time that Amazon was offering S3 and EC2. So we were just seeing the very beginnings of the cloud, but we're not at that point yet. The servers are physical machines. Yes, VMware had been around for a while. There was virtualization, but for this particular type of problem, the solution was built around physical devices. And when you have thousands of servers off the shelf, there will be failures. Some of them will fail each year. And so you have to be able to develop in such a way that you can deal with failure. You can anticipate that there will be failures. You may not know which server will fail, so you have to be resilient to that kind of failure. Now, the high-level architecture for Hadoop has two types of nodes. At the very top, we have the name node. The name node is the master controller for everything. It is the interface to the outside world. On this name node, we have a lot of very powerful technology. What happens is we're going to accept requests and code from the outside world into the name node. And then the name node's job is to figure out which of our thousands of servers available to us are going to be available to process this particular bit of code. So that's the name node's job. The data nodes are the other type of node. They'll receive that bit of code. They're going to run that code locally with the data that they have and send the results back. The name node will then send a message back to the consumer and say, hey, your data is now available. Here's where your data is. The way that this file processing works is the Hadoop distributed file system. This is a Linux-like file system, and what we do is we take very large files and we break them up into discrete sized chunks. Typically, that'll be 64 to 256 megabytes per chunk, but you can change the size of those chunks. What I have down here is an example of that kind of processing. So we start with a giant data file. Maybe that's a couple gigs, maybe it's a few terabytes. There's quite a bit of range in there, but the process works the same regardless. Every one of those files is broken up into discrete chunks. And here I have 4 such chunks. What then happens is that those chunks get allocated to each of our data nodes. So I have 5 data nodes in my example. And there's an algorithm that will push chunks of data out to different nodes. I'm not going to get into details on exactly how that algorithm works, but at a high level, what it does is it will allow you to process data across different servers. So we replicate the chunks to different servers, and we don't overwhelm the same servers with lots of chunks. So you see chunk 1 is on servers 1, 2, and 4. Chunk 2 we put on servers 2, 4, and 5, and so on. That way, when a request comes in from the name node that says, hey, I need to process giant data file with some code, the name node can realize that, well, chunk 1 is over here, and we're going to get chunk 2 from here, we're going to get chunk 3 from here, and we'll get chunk 4 from here. And then the name node can pass in that code to each of the servers that are receiving. Each of the receivers of the code will be able to process that code and will be able to do it against a small chunk of the data. Notice that server 2 is not part of this particular query, so it does not get that code. It remains available so that if somebody just needs to process another bit of giant data file, we might use server 2 for that processing. So the name node is responsible for figuring out which of the data nodes will get code to run against their local data. And the data nodes are responsible for taking that code and running it. HDFS is append only. What that means is you can take an existing file and you can add more rows to it, but you cannot modify those rows, nor can you delete rows from a file. What you would have to do is delete the file itself and reload it with a new file. This leads to one of our first architectural decisions, and that is around how big those files ought to be. Ideally, you'd have very large files that have lots and lots of data in them. That way they can be segmented out efficiently and processed most efficiently across a large number of servers. But it comes at a cost that if you need to modify your data for any reason, well, now you have to delete and reload a very large file. So typically what we'll do is break it up into smaller partitioned chunks. Maybe we partition it by day, by month, by week. Maybe we have several large files in a single day. Maybe we have one file that handles several days. We could also wait until a file gets to a certain size and kind of cap it at that certain size. There are a number of things that we can do to try to keep this process moving smoothly, where we deal with the trade-off between this file size is too big to reload quickly versus this file size is too small to distribute and allow for multiple servers to process efficiently. So we talked about the hardware side and HDFS. Let's now talk about the software side. During this time, remember we're on Linux here, the most popular language is C. Java is the most popular, relatively easy language. And one of the benefits that Java had over C is if you're in a server system and you've got some HP servers and some Dell servers and some IBM servers, well, you don't have to write different code to have them run Java. You just write the same Java code and it doesn't matter if it's an HP server or a Dell server. It'll still run. On the C side, there's a chance that you will have to recompile that code and there may be things that are optimized for an HP blade as opposed to a Dell blade. So that cross-compatibility can be a potential concern. With writing Java code, that's easy. You know that it's going to work. That was kind of the main benefit that Java provided when it came out. Next, we know that servers at this time have a relatively limited amount of RAM. Today, we could push 2 terabytes of RAM into a server. It's not that cheap, but certainly feasible. However, at that time, 2007, you're lucky to get 64 or 128 gigs of RAM in a server. So we have to write code that assumes that we're going to be processing files that are much larger than the RAM we have available, which means we're going to be doing a lot of disk operations. That means that we're going to probably want to keep the code local to the direct storage that holds our data. That way we're not moving much data across the network, because networks were also capped pretty tightly at this point. Today, you may be able to get dual 40 gigabit fiber channel relays in your servers. And if so, that's awesome. You are pushing a huge amount of data per second. Back in 2007, think about more like 1 or 4 gigabit. So now you're pushing 125 megs a second, maybe 512 megs a second of data through a server. If we're talking about a 2 terabyte file, that's a pretty long time to wait. So instead, we want to take code, which at its biggest is only a few hundred kilobytes or maybe a couple megabytes. We're going to take that code and we're going to push it down to the individual data nodes. That's a lot less network bandwidth utilization, and it allows the data nodes to run locally against the data they have, do their processing, and send up smaller result sets to a server where it can be accessed by end users. So with those hardware constraints, we also have something that's a bit interesting, and that is around data structure. We're making an assumption that developers will know the data context when they write their code. They will know what the data looks like and also what specifically they need to understand about the data in order to run their query. This leads into one of the main concepts of the Hadoop paradigm, and that is semi-structured data. If you're familiar with a relational database, you're familiar with a very structured set of data. And the closest comparison to Hadoop in the relational data space might be a Kimball-style data warehouse. So in a Kimball model warehouse, you have facts, which help us explain specific metrics. And then you have dimensions, which give us detail about those metrics. They fill in the blanks. Well, both facts and dimensions are very structured in the sense that every row that gets inserted must have a particular format. We have specific data types. We have whether or not the value is nullable. We have check constraints, default constraints, primary and foreign key constraints, unique key constraints. We have all of these different types of constraints that force the data to go in as we expect it to go. If somebody tries to insert a row that doesn't fit that format, we throw it away. There's a bouncer at the door that says, no, you are not allowed to go into this table. By contrast, Hadoop has no bouncer at the door. Any record can be written into a file. Then, when it comes time to retrieve the data and process it, the developer has to understand what correct data looks like and be able to handle data that is not correct. So here's an example of what I mean. This is semi-structured data in action. And there are two scenarios where semi-structured data can really be beneficial. The first scenario is, suppose we have a log or some other file where different lines can have different sets of values. They have completely different data shapes. Hadoop can process this very easily. A relational database cannot. We would have to transform the data and standardize it so that each row follows the same pattern. With Hadoop, we can ignore the rows that don't follow the patterns we want or deal with it some other way. Also, sometimes we may need the data in a different format. Here's an example of a log file that I created. We may have two separate applications. The first application is looking at critical errors, and so everything that's marked as error here. And what we want is the error code and maybe the name of the user who was associated with that error. So we have these errors and we can process them. Meanwhile, we may have another application running, churning against these same files that just wants to figure out how many warning info and error messages there are over a time period. So we need to know the time period and we need to know the type of message. There could be other applications also processing this data at the same time. The important point is, when it comes time to process, the developer assigns the structure. The way that we develop, going back to this 2007 era, is MapReduce. MapReduce is built off of two functional programming constructs. There's mapping and there's reduction. Mapping, if you want a relational database, a SQL context, think of it as similar to your select statement, your where clause, and your order by clause. Technically, that's not quite right, but it's close enough for purposes of this talk. Reduction, think of it as your group by and having clauses. So mapping is filtering and sorting data, and then reduction is aggregating data. Hadoop combines map and reduce operations into a chain, and we can use those in order to get a result set we want. All Hadoop result sets are fundamentally key value pairs. So it doesn't matter how the data comes in, what we get out is a key value pair. Everything that gets stored in between is a key value pair. So we're working with key value pairs. There are plenty of elements in the Hadoop ecosystem which will simplify for us that structure. So in Hive, I can write a HiveQL query that will take that data and will project it as a result set. That's a way of simplifying for us the process. Here's an example of MapReduce in action. Let's suppose that we run a large retail store, and this is probably about 10 years ago, back when we had large retail stores that tended to sell a lot of electronic items. And we sell media, DVDs, Blu-rays, CDs, VHS cassettes. So we have all of these different types of media, and we have a lot of details about those media. We have the title, the price, we have the time that somebody bought it, we have the specific medium, we have the SKU. We've got all of these different things, and that's all stored in big files. But today, all I want is to know how many of each media type was sold during a particular time frame. So I'm going to write some code in Java, and I'm going to send that code to the name node. The name node will then analyze the data set that I'm interested in and realize which servers that data is on. So it'll realize that this is the data that we want, and that data is already broken up into a number of chunks across several servers. The name node will then send my mapping code to one or more data nodes. So these are data nodes. The first data node may have the first two chunks that I'm interested in. This bottom data node may have the last two chunks. And the middle data node has the third chunk. Each one of those data nodes performs a map operation, that is filtering and sorting the data. What we want is to get a set of data that is where the key is the media type and the value is something. Because I'm aggregating, I'm just getting a count, that value, it's fine for it to be just a number 1. So the map process, we're going through each line of the file and we're spitting out a key value pair into what is called intermediate data. Then, in the middle here, there's a process that's called shuffle and sort. I don't particularly like the term shuffle and sort. I would prefer it be something called like sort and deal, because what really happens is you're shuffling up the data. You're really sorting it out by the key, and then the name node will deal that data out to reducer nodes. So these reducer nodes get the reduction code that I wrote, and they will take that code against a set of key value pairs and then process that. Here, the name node will pass along to the first reducer the terms Blu-ray and CD. So the reducer is responsible for running this reducer code against Blu-ray and CD records. And that's across the entirety of this intermediate data. Now mind you, this reducer node might be the same as one of these map nodes, or it could be a totally different server. It depends on a number of factors, including how well loaded down these servers are. Regardless of which server it is, eventually each reducer is going to take its responsible keys, perform the aggregation, and then spit out the results as a key value pair. After each one is done, we finally have our output data. And our output data is stored in one or more files wherever the developer said to put those files. The developer is then responsible for concatenating all of these together, aggregating the data however that he wants, and then displaying it to end users. So that's MapReduce. The primary downside to MapReduce is that it takes a lot of code to get any work done. So if I write a Java equivalent of a join in MapReduce, that is about 1.5 pages of Java. That's a lot of Java to understand, just to do a simple join. Very quickly, other organizations realized that, Java may not be the best final language to write Hadoop ecosystem products in, and they put extra languages on top of Java to work. One of the first ones was called HBase. So this was created by a company named PowerSet, and HBase is a NoSQL, non-relational data storage engine for Hadoop. Its major benefit was that it would allow you to do near real-time data modification. PowerSet released HBase in 2008, and one of its first uses was powering Facebook Messenger. So if you ever chatted with somebody on Facebook, anytime after about 2009 or 2010, you were using HBase. The way that HBase allows for near real-time data modification is that it actually stores some of your data in memory and then eventually flushes that to disk. So that way you don't have to worry about that data in HDFS. It's not deleting and recreating files constantly. Yahoo at this time developed Pig. Pig is an ETL language specifically designed for Hadoop. So it's a procedural language. You take dataset, load the dataset, perform operations, store the dataset somewhere else. What it does is it will allow you to write in just a few lines of code what it might have taken hundreds or thousands of lines of Java code to do. Facebook was working on Hive. At this time, they had a bunch of business analysts. They needed to be able to query data, but instead of having the business analysts all learn Java, instead, Facebook decided to write a layer on top of Hadoop that would take SQL and translate it into MapReduce jobs. So the business analyst could continue to write in the language they needed to or they wanted to. It would get translated to the language that MapReduce actually uses to process, and the results would be displayed like a SQL result set. So Hive is a warehouse. It's not really meant for inserting a bunch of data. It's not meant for immediate transactions, particularly at this time. It definitely was a batch processing, let this thing run all day, but when it comes back, it'll have your result type of warehouse. Nearing the end of this phase, Doug Cutting leaves Yahoo and goes off to form Cloudera. That happened in 2008, so not too long after the initial releases of Hadoop. Following him, MapR is formed, so the first real Hadoop competition is MapR, formed in 2009. A bunch of developers left Yahoo in 2011 and founded Hortonworks. These are the three primary players in the Hadoop space. Last metrics I heard, Cloudera and Hortonworks were both about 40% of the marketplace. MapR was a big chunk of that 20% remaining. So now let's move to the next section. We're looking at the era of 2012 to 2014. This is when Hadoop really hits the mainstream. So up to this point, Hadoop had mostly been in the space of very large companies that had specific problems that they needed to solve around batch processing of gigantic amounts of data. Then, Hadoop becomes the next big thing. I'm using the Gartner hype cycle to demonstrate a fair portion of my talk today. So we started out early on in the technology trigger phase. These were the two MapReduce papers that led to Hadoop's development. We build up into, by what we get in 2012, the peak of inflated expectations. This is where CIOs started getting copies of CIO magazine that mentioned Hadoop as the next big thing. You got to go Hadoop all the things. So the CIO gets off the airplane, goes to his staff and says, I need to Hadoop all of the things. Here's a sack of money. Go Hadoop them all. Well, during this time, we see a lot of development in the space of trying to integrate Hadoop with existing corporate technologies like relational databases, things like Memcache, and other sorts of databases that are developing during this time frame as well, because the CIO says we got to go put Hadoop in. Sometimes that's a really smart idea, sometimes it's not as smart of an idea. But our mental frame to keep in mind on the hardware side hasn't really changed much throughout this era. We still have off-the-shelf servers with direct attached storage, but we're moving towards SANs. We have spinning disk, but we've got SSDs coming in. We have on-prem servers, but by 2012, EC2 and Azure VMs are starting to get better. Well, servers are physical machines, but VMware and Hyper-V are a serious technology for corporations. And we still have some expectation of server failure, but these servers are getting more expensive. We're expecting them to last longer. So I have a lot of hedging my bets here. That said, the hardware, at least in 2012, still practically the same as what it was going in that previous 2007 to 2011 period. We're on the precipice of major change. We haven't hit that point quite yet. So a lot of the development during this time was not so much changing Hadoop, but instead linking Hadoop with what you've got already. So the first technology that does this is Storm. I consider Storm innovative. It was well ahead of its time, in my belief. This was the first real-time processing system for Hadoop, and its first release was in 2011. Storm would allow you to take data from a source, and that source might be a relational database. That source might be from a web call. It could be from a syslog server. Whatever the source, you take it and you run it through what they call bolts. Bolts were Java methods that you could run and would transform a record of data in real time, and then eventually you had sinks where the data went. And that might be HDFS, That might be into a Hive store. Maybe you take it back out to a relational database, or you write it to a flat file that goes into S3. You had a lot of different options for how you could write out that data. So this was ahead of its time, but it suffered from one major flaw, and that is everything was written in Java. As we'll see later, the streaming technologies that have taken off, you don't have to write Java everything. So there are good alternatives. But again, Storm was innovative, so I give it definitely credit for that. Scoop had two major functions. The first major function is we want to be able to take data from a relational database and put it into Hadoop. That might be dumping a table entirely. It might be dumping a view. It might be writing a query and dumping. However we want to get this data, we know that we want it in our Hadoop cluster. We want it in HDFS or maybe in Hive. Second, we want to be able to take data from Hadoop, so HDFS or Hive, and load it into a staging table in our relational database. I want to emphasize staging table because Scoop is good at inserting a bunch of rows. Scoop is fine with updating a bunch of rows, but it seems to be a lot less fine with inserting some rows and updating others. That causes problems. So instead, dump it all into a staging table and use your native SQL Server or Oracle or Postgres or whatever functionality to get that staging table data into your primary system tables. Finally, let's talk Flume. Flume is a tool that was designed to ingest log data. So similar to Scoop, it was released in 2012, and also similar to Scoop, it has a specific purpose that integrates with the rest of your corporate environment. Here, you're primarily focusing on I'm pulling data from a syslog server or log files that are sitting on a share somewhere or sitting on a set of servers somewhere. I'm piping these into Hadoop via a real-time transformation engine. That transformation engine can allow me to filter out records I don't care about, might be allow me to add some useful metadata if I do care about this particular record a lot. Whatever the case may be, Flume will let me take the data, do some quick transformation, and then write it to a sink. Again, probably HDFS, maybe Hive. So those are the primary technologies that we used to integrate data in our current corporate environments, getting it into this new Hadoop cluster that everybody's got to have, everybody's got to love. It's going to solve all of your problems. More on that in the next section. So now let's move on to the era from 2014 to 2016. To this point, we mentioned that the hardware hasn't really changed, but we were on the edge of a major change. This is when we start seeing those major changes. More companies adopted Hadoop. That CIO had his copy of CIO magazine that said Hadoop was going to solve all your problems. Well, it's a couple years later, Hadoop hasn't solved all of the problems, and we moved down from the peak of inflated expectations. We're getting down into the Trough of Disillusionment. This is the point where there are a lot of papers coming out in the computer science space where the concept of the paper is, well, I can solve problem X better with this technology than I can with Hadoop. And somebody else writes a paper that says, I can solve problem Y faster than you can with MapReduce. And somebody else writes a paper, I can solve problem Z faster with this technology than I can with MapReduce. And you have this stream of papers. Each one of them on its own is true, but it misses a big point. And that big point is Hadoop and MapReduce are in all of those cases, as in you have a viable solution for all of those cases. But technology X, technique Y, technique Z may only apply to a certain subset. So this is where we temper our negative expectations during this time. But that was a less popular opinion. So we're moving down into the Trough of Disillusionment. The reason that we're moving down, in large part, I think, is because the hardware paradigm shifted significantly. We now have, for the Googles and Facebooks and Microsofts of the world, servers specifically designed for those companies. It's no longer off-the-shelf purchases. Now it's specifically designing this particular blade that will work exactly as I want it to. We're moving to SSDs on SAN and on a storage area network as opposed to direct attached storage. The Hadoop distributed file system ends up being kind of a liability. And the reason that I think it's a bit of a liability is your SAN admin is saying, wait, you're storing how many copies of the same data on my SAN? I only have 50 terabytes of data available, and you want to copy the same 2 terabyte file multiple times? No, that's not how it works. It may work on your direct attached storage that way, but in my SAN, I want 1 copy. Servers have more memory as well. 512 gigs is no longer out of the question. Even a terabyte you can find at this point in time, especially as you get closer to the end of this era. Servers are mostly on-prem, at least the ones that we're talking about in these Hadoop projects. We're starting to see some platform as a service offerings in Hadoop around this time, but serious Hadoop installations tended to be on-prem. And with on-prem, though, we're starting to see some virtualization. Instead of using physical hardware for everything, we're building VMs and running our name nodes and data nodes on VMs. That changes the Hadoop landscape as well, because instead of having physical servers that had direct storage, now you have VMs sitting on a SAN. Previously, a benefit of Hadoop was you kept the data and the compute close to one another. So the compute was against subsets of the data. Well, now when every server is equally distant or near to the data, you don't have quite the same costs of shuffling data around because it's all going on the same SAN. You don't have quite as many costs of having different servers process the data because they're all reading from the same location. So without that absolute nearness of the data, we see the way development techniques work have changed a bit as a result. Some of these changes, though, especially that one about going to SANs and VMs, it was a little bit tricky to pull off. A major stress point is that HDFS assumed that you break a lot of data across a bunch of drives. Well, like I mentioned, that SAN admin doesn't want you doing that to his SAN. Those are expensive disks, especially if they're SSDs. So SAN admins didn't want that. They want you to cut the replication factor down to just keep it 1 copy. Virtualization, a little bit of a conceptual challenge around that pathing, that loss of speed because you're no longer reading directly from disk, direct storage. But with Hadoop being more stable hardware, being on faster hardware, those corporations that spent millions of dollars putting in a Hadoop installation, they want this stuff to be faster. It's no longer okay to wait 8 to 12 hours for a report to run. They want the report in a minute, 2 minutes. Sometimes they want it immediately. They want it real time. And as a result, we start to see the next wave of Hadoop ecosystem technologies. One of the first ones is Apache Tez. So Tez was built on top of MapReduce, and it builds a direct acyclic graph, a DAG, in order to reduce the number of map and reduce operations necessary. Also, reducing the amount of times you write to disk and read from disk. This is now readily available in Hive. It's just built in, and you can get up to a 3x performance increase in a realistic production scenario because you're no longer reading from disk every time you start a process and writing to disk every time you end. If you go back to that image of what MapReduce looked like, every step along the way we're writing to disk. So we write that intermediate data, then we read that intermediate data, process it, write it, read it, process it, write it. With TES, we're trying to do fewer of those operations. Along those lines, a few really smart guys down at Berkeley came up with Apache Spark. The Spark paper itself is a nice read. It's pretty interesting. It's relatively easy to read as a computer science paper goes. But I consider it the single biggest product to come out of the Hadoop ecosystem since Hive. Hive is probably the single biggest product because it had more years to run through the process. It had more years for people to adopt it and to use it. Spark has been around since about 2013, but during that time, it has become a dominant paradigm in processing. The reason is Spark ends up being way faster than MapReduce. Ideally, all Spark operations happen strictly in memory, and we use a concept called resilient distributed data sets in order to facilitate that. So these RDDs allow multiple servers to process the same data set in smaller chunks in memory independently of one another. But still, in the event that a server fails to complete, or a server has some sort of issue in the middle, or a server never received a message to process, there's a central agent that can have another server pick up that slack. It's a resilient data set that is also distributed across a number of servers. So Spark was written in Scala, and Scala is still the primary language for Spark. Scala is a Java-based functional programming language, and if you're not that familiar with Java, but you do have some knowledge of functional languages, Scala should be fairly easy to pick up. If you're not a fan of Scala, there are typically APIs for Java and for Python in Spark. There are a couple of places that Scala APIs are better than Python and Java, but now, by this point, we're in Spark 2.0 and later. It's mostly feature complete for everything. Also, there's a library called Spark SQL. That's SQL on Spark. You can write SQL statements and have them process against a Spark cluster. And if you're familiar with R, well, there's a machine learning library called Spark R. Spark R is built into Spark and will allow you to run R jobs against entire distributed data sets. Historically, R has been a single server, single memory, often single CPU language. Being able to change that and distribute your load across dozens of servers is major. So if you're not a fan of Spark R, there is a community version of that library called Sparkler. I actually kind of prefer Sparkler over Spark R. I think the interface is a little bit easier for people to understand, to get into. Regardless of which library you choose, though, this is a cool way of getting past a major limitation in R. While Spark was working on getting significantly faster, and by significantly faster, their claims are roughly 100 times MapReduce. In practice, 10 to 30 times MapReduce is what I hear. That's a pretty big change. That's pretty huge. Well, during this time, the Hive developers have not been sitting on their laurels. They've been working hard as well, and they came out with Hive LLAP, which is Hive 2.0. This is getting Hive closer to real-time querying. It's not a transactional system, still not a transactional system, but it's closer to a real-time warehouse than it ever was. Original Hive used MapReduce, lots of processing, lots of time to create batch jobs. With TES, you get that speed improvement of a few X, but with LLAP, it's low latency analytical processing. You're talking milliseconds instead of seconds or minutes. You can also integrate it with Apache Druid. Now, Druid is still pretty early in its development. It is a column store data with inverted indices. And what's really interesting in all of this is the way that it works. You have a fact table, And in that fact table, we're going to have some dimensional data, and we're going to have some fact data. The way that a classic dimension works, a Kimball-style dimension, is you have that dimension link, and we're going to have a dimension table that has all of the records for the dimension in question. Well, Druid kind of inverts this a bit, and instead of having a dimension and then you link it on the facts table, think instead of you have a dimensional record and then you have all of the fact records associated with it. You have another dimension record, you have all the fact records associated with it. So now, when I need to aggregate, get the sum of values where the dimension ID is 1, it's a lot easier, it's a lot faster to aggregate this data over here in Druid than it is to take a bunch of data here, filter it out, sort it. Maybe I have to join to the dimension and then be able to process and answer your question. Druid is not a general purpose solution because, for example, they don't do joins. So you can't join multiple tables together in a Druid query. That said, for the types of queries that Druid was designed for, its performance is fantastic. I also want to talk about Kafka. I'm a huge fan of Kafka. LinkedIn, JKreps, released Kafka in 2011, but it really took off a few years after that, and that's why I'm including it in this section as opposed to the prior one. Kafka is, at its core, a message broker. It sits on the Hadoop stack. Its job is to receive messages from producers and eventually get messages to consumers. And the major benefit of Kafka is that everything on that space is distributed. So I have an image here, and let's walk through this design. On the left-hand side, we have producers. Now, producers have one goal: send data and have somebody do something with that data. Once they send the data, they don't really care anymore. In the middle, we have Kafka brokers. Brokers will take that data and store it. Specifically, they store it in what we call a topic. Each topic is just a storage point for data. It is a logical container that stores a particular type of data. Inside the topic, you have one or more partitions. Partitions are the physical storage, and you can think of it as individual files. And if you want to think of a metaphor, your topic is a folder, the partitions are individual files, and each file is owned by one of the brokers. So each of the brokers can have copies of the file. Not all of them will have copies of every file, probably, but you could set it out that way. Similar to how not every MapReduce node, not every HDFS node will have a chunk of data from a particular file. Not every Kafka broker will have a partition for every topic. Regardless, you store data in these partitions. Then consumers come and they want to take the data away. So consumers can process this data, and we have grouped together consumer groups. The consumer group allows multiple consumers to read from the same data source, that same topic, independently of one another. And that way, if you need to get faster processing of the data, you could spin up more consumers to read that same data and you'll go faster. So it's a linear scaling for pretty much everything in this space. The way that works, how we can get there, is based on the metaphor driving Kafka. Typically, a message broker acts like a queue. So we have a consumer whose job is to pull messages off of the queue. Pull the message off the queue, you process it, you consume it, and now it's consumed, it's gone. Pull the next message off the queue, and keep going. Meanwhile, a producer is adding messages to the queue. By contrast, Kafka follows a log model. So here, producers are inserting records. Think of it as you're inserting a record at the end of the log. So you're inserting new rows into a log file. Each consumer starts at the beginning of the log file and starts reading forward. So a consumer will read a message, then it will go to the next message. Read that message, go to the next one. Now, what's cool about this is the consumers cannot modify those messages. What that means is that consumer 2 over here can act independently of consumer 1. We can have different applications independently reading through that set of data. We can have different microservices whose entire function is to do some tiny thing, knowing that they will read the same data source, but never having to worry about somebody modifying that data. Another interesting feature is, let's say we found a bug in consumer 2. That data is totally wrong. Well, we can fix that bug, maybe consumer 2 sub 1, and have it start from the beginning and have it read across. Consumer 1 didn't have a bug, so it can just keep going. It can process data just how it normally would. We can keep certain parts of our application running independent of other parts of our applications. So that's Kafka in a nutshell. If you want more, I do have a link to an entire Kafka talk that I do. So I'll give you a link to that at the end, as well as some other source notes. So now let's get into the present day. We're looking at 2016 and later with streaming and cloud technologies. We've moved beyond the Trough of Disillusionment, and we're starting up this slope of enlightenment. We haven't quite hit the peak, but we're starting to get back up there, especially because we're seeing another shift, starting with Kafka and moving into a new space, working with IoT. So this on-prem paradigm has significantly shifted yet again. And now we've gone from having one major Hadoop hardware setup to several. We still have the big hardware, high-quality on-prem servers, but these are virtualized. These are loaded with a lot of RAM, a lot of CPUs. They're probably running on flash arrays. They're almost certainly running on SANs. And we're using Spark primarily. So those are our big churn servers. But we also have a bunch of smaller endpoint servers. So think about IoT devices, refrigerators that need to connect back to the internet, or Raspberry Pis that are collecting data in various places and sending it up to our servers. We may have tens of thousands or hundreds of thousands, millions of these devices that are all sending messages back, maybe every second, maybe every minute. Well, at the larger scales, we're processing millions of messages per minute. Almost definitely. We may be processing millions of messages per second. And in order to handle that, we need something like a Kafka to absorb that level of hit. Cloud servers are another technology for us. We may be able to run a Hadoop cluster entirely in AWS or in Azure. We're using medium-sized to large amounts of RAM and compute. We're probably using something like Elastic Block Storage or Azure Storage. And the full backing, the underlying backing of what's under there, probably S3, Azure Blob Storage. Prior to this time frame, I know that Amazon especially warned heavily against using S3 as a data store for Hadoop. And I think it's still valid. Like, you don't necessarily want to process your Hadoop cluster strictly from S3. You might want to have it in EBS because you'll get better performance. You'll have lower latency. There are cases where in S3, because it's an eventually consistent file storage system, you might have files that you added in which aren't available yet, and so processing just won't know that they exist. So you'll get inconsistent results. On the development side, we now have Docker containers. Containerization has become the big fad of 2017. And of course, Hadoop is going to be able to fit into Docker. So this is an era of specialization. We're not looking at one hardware setup. We're looking at a bunch of hardware setups. Memory is at least as important as disk at this point. Spark has become the default. MapReduce is a lot less popular today than it was 3 years ago because Spark is just so much faster. And what we're seeing is this, not necessarily an abandonment of MapReduce, but we are seeing mechanisms to process faster within the MapReduce paradigm and mechanisms to avoid MapReduce if we can get it faster than that. On the other side, so we're seeing bigger, more powerful hardware running bigger, more powerful Spark clusters. Well, we also have those Raspberry Pis and those smaller IoT devices. They can be running a tool like NiFi. NiFi is a sort of an ETL tool. Its nicety is, if you're familiar with Informatica or SQL Server integration services, those technologies are UIs for performing ETL. NiFi, similarly, has a UI for performing ETL. One of the NiFi advantages here is that you can get a small version of it called MiniFi that will fit on a Raspberry Pi 3. So your actual IoT device can be running Hadoop and sending messages up to a big server also running Hadoop. Streaming has become a vital portion of the Hadoop names area. So there are several streaming technologies that have become popular over the past couple of years. We started off by talking about Storm, which was released in 2011, but it was Java everything, and that limited its adoption. Now there are 3 primary competitors for your streaming space. The first contender is Spark Streaming. This uses micro batches of data. And what I mean is we may wait for a few milliseconds, collect a small amount of data, and then perform some Spark operations off of that. We build resilient distributed data sets for those small amounts of data and process them. So it's not truly real time, but typically it's close enough for what we want to do. If you do want something closer to real time, look at Kafka Streams or Apache Flink. Both of those are top-level projects. They're both very interesting solutions. Kafka Streams is a part of Kafka, and Apache Flink it lives on its own. They're both single-row, real-time processing engines. And the only significant trade-off that I see is you probably, if you have more of a data science solution, you're probably more interested in Kafka Streams. It's easier to get an ad hoc stream going. By contrast, if you're more of a central IT type, you might prefer Flink because it's better for centralizing control. It's better for trying to keep in control what's going on a particular cluster. Otherwise, it's like 6 of one, half a dozen of the other. So they both work very similarly. They both work really well. And even I'd throw Spark Streaming in there. If you're a fan of Spark Streaming, that's cool. All 3 of them are viable technologies. The other space that's really been affected in Hadoop within the last couple of years is a move to the cloud. We're at a point where it is viable to run your Hadoop cluster strictly within AWS or Azure or Google or wherever, whichever cloud you're interested in. You're probably more likely at this point to deploy a cluster in the cloud than you will to put it on-prem. Maybe you bring a cloud cluster back on-prem once it gets really big, but for the pilot clouds, for the smaller ones, yeah, you're probably pushing it up to a cloud. In the cloud space, there are a couple of platform as a service versions of Hadoop. The first one that I'm going to talk about is HD Insight. This is Microsoft's version in which Microsoft and Hortonworks partner together. HD Insight is Hortonworks' data platform running in Microsoft Azure. It is a platform as a service offering. So what you do is you connect to the Azure portal. You'll select the cluster that you want. There are some pre-configured clusters, like one that will include Spark, one that will include Kafka, one that includes Hive and Pig. You select the cluster that you want. You kick it off, it builds up, takes a while to build up all the servers, to deploy the software, to configure them. But once you're done, you have a cluster. You can do your work on that cluster, and when you're done with that, delete it, get rid of it. You no longer need that compute. You can keep the storage. Maybe it lives in Azure Blob Storage. Then, next time you need a cluster, repeat the process. On the other side, Amazon has Elastic MapReduce. Elastic MapReduce started from a MapR distribution, and I believe you can still select a MapR distribution, but Amazon has created their own distribution of Hadoop based off of MapR and then modified to do what they want it to do. They offer this up as their platform as a service product, and Elastic MapReduce is functionally similar to HDInsight. The mechanics behind how a developer works with it are a little bit different, but it's pretty similar. It's a little bit less expensive, though it tends to lack some of the client tools that you'll get with HDInsight. And there are benefits and costs to each one of them. I don't think that either one is a killer reason to select one cloud service provider over the other. Instead, I'd say if you're primarily an Amazon shop, use EMR. If you're primarily an Azure shop, use HDInsight. If you're split between the two, use whichever one solves the problem that you need easier. So if you're going to be running Hadoop in the cloud, S3 and blob storage are good spots for data. You don't really need HDFS anymore. At least you don't need a specific HDFS environment. You can get away with long-term storage in that S3 or blob storage, bringing it into EBS or Azure storage as you need to process. You can spin up clusters at will. This is regardless of whether you're in Elastic MapReduce or HDInsight, or if you have IaaS products. You have a bunch of VMs that you build your own Hadoop cluster out of. Spin up your cluster, do your processing, get rid of your cluster afterwards. Unless it's a 24/7 cluster processing scenario, and some cases that would make sense, but for one-off jobs, like I'm building daily reports and I know that it's going to take 8 hours. I don't need those servers the other 16 hours. You can get rid of them. Clusters can live independently of one another too, so I may need 6 servers to do that. And I could have a totally different 6-server cluster that solves another problem. And I may have a 30-server cluster that I just have running 24/7 because maybe it's driving analytics from my website. Maybe it's accepting all of those IoT messages and then doing something with that data sometime later. If you do use the platform as a service product, do be aware that no matter which of the products you use, they will close certain ports. For example, HDInsight will not open up the web HDFS port. That's port 50070, and you use it to connect, say, through a browser or through a device, and you want to perform some sort of HDFS command, like I'm going to push a file up into HDFS, or I'm going to pull a file from there. So that's your web interface. Well, HDInsight keeps that port closed. They will allow you to use web HCAT, which is a Hive catalog port, but it's not the same. And also, neither solution supports Polybase. If you're on the SQL Server side of things, your primary relational databases are SQL Server, Polybase is a big deal, and we'll talk about that in the next section. But first, I want to tell you about Cloudbreak. So Cloudbreak is a Hortonworks tool, and it's designed to deploy and manage a Hortonworks cluster up in AWS, in Azure, in Google, and even OpenStack. So the whole point behind Cloudbreak is you can decide that today, because the prices are cheaper, I'm going to put this cluster up in AWS. And the next day, maybe the prices are cheaper in Google, so I'll put it up in there. The data will live in both places, and maybe I already have teams that prefer AWS and some teams prefer Azure. Perhaps my data scientists want to be in AWS because they like the image recognition libraries and they like some of the things that you can do over there over what is in Azure. By contrast, perhaps my relational database team prefers Azure because they're using Azure SQL Data Warehouse, they're using Azure SQL Database. Regardless of whatever the reason may be, that central operations team has to manage multiple clouds, and this is a tool that acts as a buffer. It will allow you to write the same code and be able to deploy a cluster to each one of those clouds. So let's now compare a Hadoop cluster to a relational database. I'm going to use SQL Server in my example because that's the example I'm most familiar with. But if you prefer a data platform technology like Oracle, Postgres, MySQL, cool. Insert that in where I say SQL Server, and most of the time it's still going to be correct. Overall, Hadoop and SQL Server, completely different technology stacks. They serve different purposes. They have different advantages and disadvantages. I do have to include a chart, and this chart is actually a bit muddier than it was a few years ago. See, a few years ago, I could more cleanly bifurcate where Hadoop ends and where SQL Server begins. But what we've seen are some technological improvements on both sides that are eating into the other side's space. Hadoop, classically, it's good for large batch processes, but it's moved into the online space with streaming. We talked about Kafka, Kafka Streams, Flink, Spark streaming. These things are online. They're kind of close to real-time processing. SQL Server has historically been online processing. And also you could do batch jobs with it, long-running jobs that return maybe a large result set or parse through a huge amount of data. The major point where they still remain separate is in structure. Hadoop is still a semi-structured data platform space, but SQL Server, other relational databases, remain structured. Though even with that, in 2016, Microsoft released a version of SQL Server that has JSON support. So now you have these JSON data types that are not strictly structured the way that a classic SQL table would be. That's not really moving SQL into the semi-structured space, but it's like this tiny edge step over, including a bit more, while still retaining that structured data advantages that you'll get with a relational database. So there are definitely reasons that I would prefer a relational database over a Hadoop cluster, and vice versa. In the relational space, you get provably good transaction systems. You'll get ACID compliance. You'll get the benefits of normalization, of constraints, of protecting your data. Basically, if you have data where if it's wrong, you're fired, I want that data in a relational database like a SQL Server, like an Oracle. I don't want it in Hadoop because Hadoop will often give you eventually consistent results, which means that as the data comes in and becomes available, your results may change. Whereas with SQL Server, that result is transactionally focused. You have atomicity, and you'll get the same result each time unless you do something horrible like go into read uncommitted mode and start reading dirty data. In that case, your job is in your hands. Now, relational databases are really good for transactional processing scenarios. Very fast, staccato, give me a few records or a single record, but I need them very quickly. They're also good for warehousing in cases where you know the questions that are being asked. This is a Kimball model or an Inman model warehouse. You ask the business people, what things do you need to know? What do you need to report to regulators, to the CEO, to the board, to your manager, to other teams' managers? What things do they regularly need to see? What are the important questions that the business needs to answer frequently? And you put that data into a warehouse where people can get to those results pretty easily. You also have a lot of people in this space. Relational databases have been going strong for 3 decades at this point. There are a lot of people who've spent quite a bit of time building up extremely good knowledge in this space. And so if you run into a problem, you're pretty likely to find an answer somewhere. So let's switch over to the Hadoop side. On the Hadoop side, if I need to aggregate lots of data and batch process that data, This is typically cheaper than using equivalent relational databases. If I want to process text data or genetic data, Hadoop, definitely over a relational database. If I want to try to answer unknown business questions, this is where Hadoop can shine with its data lake concept. I store a bunch of data of sometimes dubious, sometimes great provenance, but that data is there and I know how to access it. I kind of know what's in it, and it just sits there until somebody needs that data. But we don't know when they'll need it. We don't know exactly what they'll need. We just know that someday somebody's going to want some of this data. That model doesn't work so well in a relational database because every time there's a new data point, say there's a new column that gets added, well, we have to add it to the warehouse, we have to add it to the ETL process, we have to walk through all of these different steps to get that data. It's not so great of a solution. But in Hadoop, just add it to the file, let the developers figure it out. We also see a couple of new cases, and these are the two cases that I mentioned earlier on. Cold storage of data, so storing stuff that would normally fit in a relational database, but you don't need it immediately. Go put it over there. Go put it in your Hadoop cluster, maybe expose it through Hive, or use a technology like Polybase to stream the data back into your SQL Server instance. You can also handle large amounts of streaming data with Kafka and some sort of streaming technology on top of it. So what I want you to get out of this section is these are complements. These are not competition for one another. And I have here a few scenarios that I just thought of off the top of my head of how you might be able to integrate both Hadoop and SQL Server to solve the same business problems. Like you're taking data with Kafka, you're aggregating it with Spark streaming, and then you're feeding the data into SQL Server so that your UI developers can build components off of that data in SQL Server. Maybe you store the transactional data in SQL, and then you migrate it to a data lake in Hadoop and expose it using Hive. Or you're offloading data from your SQL Server, nightly batch processing using Scoop, dumping it into Hadoop, processing it in Spark, and you're doing some more heavy processing than you want to do in that relatively more expensive SQL Server or Oracle database. And so on. There are quite a few other cases that you might be able to think of where you're combining multiple different platforms and getting out a result that is beneficial for the business. So now I'm going to get into the last section of today's talk, and that is talking about what Microsoft is doing in the Hadoop space. On the vendor side, Microsoft has tied itself very closely with Hortonworks. Azure HD Insight is Hortonworks' data platform, and there's also some other places where you can clearly see the two have a strategic relationship. Despite that, Microsoft products will work with Cloudera, and most of it will still work with other platforms like MapR. So you don't necessarily have to lock yourself into Hortonworks if you're on the Microsoft cloud. Within .NET, there are libraries for different Hadoop cluster activities. One of them here, Microsoft.Hadoop.MapReduce, is a library that will allow you to integrate mostly with HDFS. So you can connect using the web HDFS port, that's port 50070, and be able to push and pull files. This is a nice way of taking your existing .NET code and integrating it with a new Hadoop cluster. There are other libraries around, such as allowing you to query Hive using LINQ, which is .NET's language integrated queries. So you can write fluent C# and translate that into Hive jobs. There are some other third-party libraries that work pretty well with .NET. Confluent, the company that kind of has primary maintenance over Kafka, has a .NET driver, and it's available via NuGet. There are other Kafka drivers that work for .NET, but I do prefer the Confluent driver because It's currently maintained. It has official support from the primary support and development company around Kafka. And so it also, I think, works better than the other ones. It tends to be faster than most of the others and tends to be much more complete in terms of API than some of the rest. Microsoft themselves have some cross-platform support in the form of drivers. So there's an ODBC driver, the Microsoft Hive ODBC driver, that you can install on your Windows servers, like if you have SQL Server running on it, and that will allow you to create a linked server to Hive. Over in the Hadoop space, there is a ODBC driver for SQL Server that runs on Linux. That Linux ODBC driver, you can install it on a server that uses Scoop and be able to communicate directly with SQL Server via the Microsoft Linux ODBC driver. Within SQL Server Integration Services, there is some limited support for Hadoop. You can run Hive jobs, you can run Pig jobs, you can migrate data using WebHDFS or WebHCat. I do prefer WebHDFS over WebHCat because I want to be able to do more than just work with Hive. But anyhow, that is available within integration services. Polybase is Microsoft's newest technology for connecting to remote servers. It started out in about 2010 and was part of Parallel Data Warehouse, and it was SQL Server connecting to Hadoop, writing MapReduce jobs. Since then, it's expanded to include connecting to Azure Blob Storage, and that way you can write out to files up in Blob Storage and then read them back. The nice thing about Polybase is that this is all through T-SQL, so your SQL developers can create external tables, and then when people want to query those external tables, it's just a two-part normal name like any other SQL table would have, and you can get to the data. Your end users don't have to know where the data is located, that it's actually in a Hadoop cluster or it's actually in blob storage. They don't have to care about that stuff. One of the other advantages that Polybase gives you is, suppose you do have a large amount of data sitting in Hadoop that you want to expose via SQL Server. But you don't necessarily want to pull all of that data from Hadoop, process it in SQL Server, and then send it back to the user. Let's say you have a very precise filter that only brings back a few of the records. Well, you can push the predicate down to Hadoop. You can force a MapReduce job, and that MapReduce job will actually do all the processing. It's going to take the few records that remain, send them back through the name node to the SQL Server instance, and then expose them to the end user that way. So this is a really cool way of taking advantage of your Hadoop server without kind of scaring the SQL developers on your team. They can use the same techniques, the same technologies, the same stack that they're currently familiar with, and get a little bit more out of it. So let's wrap up by talking about some of the technologies to learn. I talked about a lot of things today, and frankly, I left out a huge portion of the Hadoop ecosystem. It can be overwhelming, especially if this is new to you, but let's not focus on trying to get all of the stack. Let's just look at some of the most important elements. I would say the first thing that you probably want to learn if you're going to come in as a Hadoop developer is some form of SQL on Hadoop. Now, for Hortonworks, I would recommend Hive. If you're using a Cloudera cluster, I recommend Impala. If you're using MapR, I would recommend Drill. All three of these are Hadoop-style SQL warehousing. So learn these early. These will be the technologies that get you a foothold. As you become more familiar, go learn Spark. And I recommend there, pick up Scala or Python, one of those two languages. That way, you can use Spark SQL, and Spark SQL works really well, but there are procedural things that you will want to do that Spark SQL makes really difficult. So know your Scala or Python, know your SQL, become familiar with Kafka and one of the streaming technologies. You can pick Spark Streaming, you can pick Kafka Streams, or Flink. All three of those are good choices. I don't think there's one that's way better than the others, but whichever one feels the best. Kafka Streams is currently my favorite. They just recently came out with Kafka Streaming SQL language. So again, it's SQL on something else. We see this trend over and over where we're getting to SQL. Finally, if you're, instead of being a developer, if you're saying, I want to go into Hadoop administration, your best friends are probably going to be Ranger and Knox. These are two of the security tools available within Hadoop. And I highly recommend you get an intimate knowledge of those because by default, Hadoop clusters are not incredibly secure. They're set up by developers who just want to get things done. And that means data might be left unencrypted. Anybody may have access, or you hard code passwords. There are a lot of bad practices out there, just like anywhere else, and you want to have tooling that will help you fix those bad practices. You want to have tooling to help you integrate maybe into your Active Directory clusters, or maybe you want to have some sort of other Kerberos-style ticketing system that you can use to connect. Regardless of what you want, those are a couple of the tools that will help you get there. If you would like to learn more about this, I have my links that I mentioned during the talk and a lot more up at csmore.info/on/Hadoop. If you have any questions at all, please feel free to reach out to me. I have my email address here and also my Twitter handle. So I want to say thank you for listening. I hope you enjoyed it.